Here we're going to be doing the integral test for convergence of series and also the p-test. So 2 tests for this video. So to motivate the idea of the integral test, let's imagine that we have a function that is decreasing, that is continuous from 1 to infinity. This will be my y. Oh, I haven't removed that. This is going to be my y, this is going to be my x, and this is going to be the function y equals f of x. So remember that the area under that curve, let's say x is going to be 1 here, more or less. The area under the curve here is going to be given by the integral from 1 to infinity of f of x dx. But you can also make rectangles of width more or less 1. So let's say the next one would be around here. More or less that width. Let's assume this is going to be 1, 2, 3, 4, 5. And let's assume now that an is going to be given by f of n. So this area here, the width is 1, and the height is going to be f of 1 plus f of 2 plus f of 3. So your area is going to be approximately equal to, not quite approximate, but let's say they're comparable, let's say, from n equals 1 to infinity of f of n. A very rough comparison, but this right here is going to be your sum from n equals 1 to infinity of the an's. So it's not that you can approximate the value of the integral with the series and vice versa, but what you can say is that under certain conditions, if the integral converges, which is something we know how to do in proper integrals, then the series converges. So let's take a look at that, what the theorem would say. So we need 3 conditions. So firstly, f is going to be a function that needs to be continuous on the closed interval from 1 to infinity. So we need that for sure. Now we will need that f be decreasing. So these are the conditions I need. F is decreasing. And who cares about f if it's not going to help us determine what the an's are, right? That's the whole point. For all n equals 1, 2, 3, and so forth. For all n's in the naturals, let's say. Then, under these conditions, the integral from 1 to infinity, and of course you can change this 1 for any n, really, you can start at any point, but 1 is good enough for us right now. F of x dx and the sum from n equals 1 to infinity of an both converge or both diverge. So they have the same behavior. So let's do a few examples. So for example, if you wanted to look at the sequence from, let's do the one where we ended last video, 1 over n. That's where we ended. Let's do it. Well, this one right here, we're going to notice that 1 over n, so 1 over x, the function, f of x equals 1 over x, is continuous pretty much at every real with the exception of x equals 0. So in particular, it is continuous on, just said on, 1 to infinity. That's condition 1. Is it decreasing on that interval? By the way, I wrote decreasing, but I didn't say where. you'd have to have an interval, I suppose. And this one, of course, if you draw the graph of f of x equals 1 over x, looks kind of like what I drew. Oh, that's very like a corner there, but it's decreasing. You can verify that. How would you verify it? You take your derivative and find the sign of it. The derivative is negative 1 over x squared. At every value of x that is not equal to 0, that's just a negative number, meaning that the function is decreasing. And lastly, well, that's just given. So the theorem tells us that the integral of 1 to infinity of 1 over x dx and the series from n equals 1 to infinity of 1 over n have the same behavior. So if we can tell what happens to one of them, we can tell what happens to both. So let's go ahead and compute this integral, because that's much easier than trying to figure this one out. All right, so to do that, we will go ahead and write integral from 1 to infinity. That came a little crooked. Of 1 over x dx, and remember, how do you compute those? You first have to take a limit as b goes to infinity of the integral of 1 to b. Who wants to be? Of that. So that just becomes the integral of natural log is the natural log of the integral of 1 over x is the natural log of the absolute value of x, evaluated between 1 and b, and then you'll take your limit as b goes to infinity. So you evaluate that, gives you the natural log, well, let's write the limit first, b goes to infinity, of the natural log of b minus the natural log of 1. Natural log of 1 is 0, so we can just not write it, just that. And of course, you know the natural log, the function increases out to infinity as b goes to infinity. So this one diverges, and therefore the theorem tells you that the sum from n equals 1 to infinity of 1 over n diverges, as I had told you in the previous video. So another example, well, let's go ahead and look at the function f of x equals 1 over x to the p. That's where the p series will come into play. P, you can pick it to be between 0 and 1, or between 1 and infinity. At p equals 1, we already know it diverges. Let's see what happens when p is greater than 1 and when it's less than 1. So the same conditions as before happen. The function is continuous, is decreasing, and if we look at the sum of 1 over n to the p, the function would match at n the same as the terms of the sum of the series. So we can do our integral and find out what happens. So the integral from 1 to infinity of 1 over x to the p. P, by the way, is not equal to negative 1, or p is not equal to 1, where we have the natural log. We already took care of that part. P is not equal to 1, or if you put it as x to the p, p is not negative 1. So that's going to be given by the limit as b goes to infinity. That's a funky b. And it's b goes to infinity of the integral of 1 to b of 1 over x to the p dx. So you integrate there, it's going to give you x to the negative p plus 1 over p plus 1, negative p plus 1, sorry, evaluated between 1 and b, and then you're going to take your limit as b goes to infinity. All right, so what does that look like? Well, we're going to have x to the, that's going to look like this. You're going to write it as 1 over 1 minus p. That term doesn't affect us in any way. And then the x to the p minus 1, because of this negative p, I'm going to put it as x to the 1 minus p. p minus 1, sorry. Changing the signs. Because I'm going to put in the denominator, so I'm going to multiply times negative. Is going to be p minus 1. Evaluated at between 1 and b, and I did not leave myself room for the limit. Well, I can do this. You cannot do it in the exam, so be mindful to write your limit as b goes to infinity. The 1 over 1 minus p, it doesn't really affect us at all. For the convergence, the value of the integral is not what matters. What matters is whether it converges or diverges. So let's go ahead and take a look at that. Well, you're going to be plugging here 1 over b, and I forgot my limit. I'm going to write it here in a minute, to the p minus 1, and then minus 1 over 1 to the p minus 1. All right, so I forgot quite a few terms. I forgot my limit, and I forgot that 1 over 1 minus p. Let's add those. The reason is because this is what really matters, but 1 over 1 minus p multiplies everything. All right, so this term is just a 1. We don't care about that. That's a 1. So that's not going to affect our convergence or divergence. It's going to affect the value of the integral. We don't care about that. The question is this one. When does this go to 0? And you will tell me, well, I have 1 over b. As b goes to infinity, this goes to 0, right? Sort of. Because what's going to happen is that this integral, actually, let me just write that limit all by itself. So let's write down this limit. Equals 1. Well, you say it's 0. Well, yes, that is true if this exponent is positive, because that puts it careful or firmly in the denominator. So if p minus 1 is positive. But if it happens to be negative, then that infinity goes to the numerator. If that p minus 1 is negative, and that goes out to infinity. Positive infinity, and that is when p minus 1 is strictly less than 0. So if p is greater than 1, this converges. Or maybe let me write it like this. Converges if p is greater than 1, and diverges if p is less than 1. At p equals to 1, we know that it diverges. So we can just throw this here. So p strictly greater than 1, this converges. And by the integral test, that tells you that series of the form n equals 1 to infinity of 1 over n to the p converge. Same thing is true. Converge if p is greater than 1, and diverges if p is less or equal than 1. So in the previous video, I talked about n equals 1 to infinity, 1 over n squared. Well, this is a p series of the form p equals to 2, with p equals to 2. P equals to 2 is larger than 1, therefore it converges. And this is one of the few that we actually know, well, one of the famous ones, I should say, where we know exactly what it converges to. It converges to pi squared over 6. All right, we'll do a couple examples, and then we will wrap this video up. Okay, so let's test for convergence, or test to see whether these following ones converge or diverge. We'll do a couple. More than a couple, a few. So we're gonna start with some like n equals 1 to infinity of 1 over the square root of n. Let's start with that. Let's do sum from n equals 1 to infinity of 1 over 1 plus n squared. For example, we will do sum from n equals 1 to infinity of, what else do we do here? E to the 1 over x squared. N. Whoops. N over n squared. And if you're in my class, this one will ring a bell because I just did the integral for that one on our review session for today. So we'll talk about that. All right. So first one, what kind of series do you have? Well, you have a p-series, just by writing it to 1/2. P is 1/2, which is less than 1. If it's less or equal than 1, it means that the series diverges. So this is just a p-series test. Right away, don't have to do anything. This one looks like a p-series. You have an n squared and you say, oh, well, I just have p equals to 2, it converges. It's not exactly the form, right? Because you have a plus 1. And so that is sufficient to ruin it for us. So what we're going to do is we're going to do the integral test for that one. So that one will turn out to be decreasing. It's going to have everything you need to have. Decreasing, continuous. So let's go ahead and look at the integral. So the integral for here would be 1 to infinity of 1 over 1 plus x squared dx. And you know that this is going to be the limit as b goes to infinity of the integral. That was a funky integral. 1 to b of 1 over 1 plus x squared dx. And this one is straight up. I wrote it just so we could compute it quickly. This is just an arctangent, right? So you get the limit as b goes to infinity of the arctangent of x evaluated between 1 and b. So you get the limit as b goes to infinity of the arctangent of b minus the arctangent of 1. Now, if you look at your unit circle, the angle that gives you a tangent of 1 is pi over 4. So this one's going to be pi over 4 here. Now, arctangent of b as b goes to infinity, well, we have to think about that one a little bit more. You have to look at the graph of the tangent that has a vertical asymptote at pi over 2. X equals pi over 2. So as x goes to pi over 2, the tangent goes to positive infinity. So when you do the inverse function, the arctangent of b as b goes to infinity is going to give you back the angle at which the tangent goes off to infinity. So that's going to give you a pi over 2. And pi over 2 minus pi over 4 is going to be pi over 4. So the value that we get matters not. What matters is that you don't get the integral diverging. Therefore, we don't know to what value, remember, but we do know that it converges. So the sum from n equals 1 to infinity of 1 over 1 plus n squared converges. Because the integral converges. That's the integral test right there for that one. Of course, I did have to mention it's continuous. The function here is continuous, it's decreasing, and it matches our series. All right, so this one right here, you look at it and you say, well, that's definitely not a p-series because this one right here is an exponential. Granted, in the next lecture, we'll learn how to do comparison test. So you could compare it sort of, it's going to be smaller than, well, it's going to be smaller than, let's see, the largest value is going to be e. So it's going to be smaller than e sum n equals 1 to infinity of 1 over n squared. This one, by the p-series test, we know it converges. So this, if this one converges, we will be able to compare this one right here as well. However, we have not introduced that idea. So we say, well, it's not a p-test. and so, or a p series, so I have to figure out something else. And the only other thing we know how to do is integral test. You could take a limit as n goes to infinity of this to, if you hope that it will diverge, but it's not going to diverge. This expression here as n goes to infinity goes to 1, and this goes as 1 over this is 1 over n squared as n goes to infinity goes to 0, so the whole thing goes to 0. So we have to integrate. Again, we have to make sure that it is decreasing, that it is continuous, and all that. And then we're going to do our integral. As I said in the Zoom session, this is limit as b goes to infinity of 1 to b, e to the 1 over x squared dx. So here we're going to do our u substitution. U equals 1 over x. That's going to give us du, which is going to be negative 1 over x squared dx. So we will have this right here matching that. So our dx over x squared becomes the negative du. So let's put the negative at the very end. That's an infinity. Doesn't look like it, but we got the negative du, so let's color that. That's my negative du. And then I get the, here in yellow, it's going to be e to the u. Well, I still have to address the endpoints. So at x equals to 1, u is going to be this here, 1 over 1, plugging x equals to 1 here, which is 1. So at x equals to 1, this doesn't change at all. Ooh, careful. I put b equals infinity. That's why it came out wrong, because it was not supposed to be there. And as x goes to infinity, u is the limit as x goes to infinity of 1 over x, which is 0. So this limit will be as b goes to 0, and let's leave b there alone. Another way you could have done is say b goes to infinity of 1 over b. If you wanted to replace it, just plug in b here. That works too. Anyways, I just changed the endpoint and left the variable alone, or changed the limit rather. Either way, you get the same thing. So negative limit as b goes to infinity of, now the integral of e to the u is e to the u. So we get e to the b minus e to the 1. Let's just evaluate it. Now as b, I did this in the Zoom session as well. I was stuck with that b goes to infinity. B goes to 0. And then this just gives you negative e to the 0, which is 1. 1 minus negative, so plus e to the 1. Just that. I don't care about the number. This is going to be like 1.78 something. I don't remember the decimal points of e. Shame on me. Doesn't matter. But this one converges, therefore, by the integral test. The sum from n equals 1 to infinity of e to the 1 over n squared converges. Wow, this today ended up being a long video. Well, apologies for that, but there was quite a bit of material to cover. All right, well, let's wrap it up here, and I'll see you in the next video.